Hello, this is Professor Herning, and this is going to be a basic introduction to the slide rule. This is a very basic slide rule, sometimes called a Mannheim-type slide rule. You can see it has a selection of different scales here. The Mannheim-type slide rule has A, B, C, I for inverse, C and D, and usually L and K. This slide rule additionally has some scales on the back for trigonometry, which we'll discuss in another video. But this scale layout it has on the front is called a Mannheim layout and is very common in inexpensive slide rules. It also has an inch ruler across the top. You can see this is a pocket slide rule where the scales have approximately length 5 inches. Now, the basic scales on the slide rule are the C and the D scale, and that's all we'll discuss in this video, so forget the rest of the scales. We're just going to look at C and D. And you can see that the C and the D scales are actually identical to each other. However, the C scale is usually on the sliding part, called the slide, and the D scale is usually printed on the base. Now, the key to the construction of the slide rule is that if you measure from the 1 on either the C or the D to the right, to a certain number, that distance is the log of that number. So log of 1 is 0, so distance from 1 to itself is 0. However, distance from 1 to 2 is log of 2. Distance from 1 to 3 is log of 3. And you know from the graph of the log function, like this, here's 1, that if you take numbers which are increasing here, the distance between them is going to bunch up on the y-axis, right? Which is why these get closer together as you approach this, which is called the right side index 1, which also can represent the 10 depending on how you think of it, and some slide rules you might see it marked as 10. This slide rule has slight scale extensions past the 1s on both ends. You'll see slide rules that don't have those scale extensions and end directly at 1 on both sides. Okay, let's use this property that the distance from 1 to x is log of x to do some calculations with the C and the D scales. The idea here is that we'll use the C scale to measure movement along the D scale, and we'll read the result of our calculation on the D scale. Most of the time you set up your calculation to read the result on the D scale, although not always when using the slide rule. But that's what we'll do in this video. Let's do this quick calculation. So I want to multiply 2 times 3.5. We'll do something where we know the answer. So 2 times 3.5 is 7. I use this logarithm property that if I add the log of 2 to the log of 3.5, I should get the log of 2 times 3.5, which is 7. So in other words, if you add outside the logarithm, this is the same as multiplying those numbers inside the logarithm. So what I'll do here is I will first set this cursor line, the large line in the middle here is called the cursor line, to the 2, the first number. Then what I will do is I will align what's called the left index 1 with the cursor line, so essentially aligning the 1 and the 2. So to multiply, you find the first number on the D scale, you align the index on the C scale with that number on the D scale, and then you move the cursor to the second number. So the cursor I'm going to move to 3.5, and you can see the result then 7 on the D scale is where you can see the result. So what you've done here is you've taken the distance from 1 to 2, which is log of 2, and you've added the distance from 1 to 3.5, which is log of 3.5, and the result, looking across the D scale, see the distance from 1 to 7, that's log of 7, right? So you see you've added physically log of 2 on the bottom here, plus log of 3.5 on the top, the C scale, and then you've read that resulting log of 2 plus log of 3.5 on the D scale, essentially undoing the log and reading 7, the result. So let's do another calculation. So here, let's do it in the same way. First, I'll find 1.6. You can see the numbers on the left end, like 1.6 6 are fairly well divided. You can see you have additional divisions here down near 1. So there's 1.6. Found it with the cursor. Then I will align the index. Then I will find the second number, the 3.4. There's 3.4 on the C scale. And then I will read the result on the bottom on the D scale, approximately 5.4. See, it looks like it's a hair to the right of 5.4, but I'm going to read it as 5.4. With these short slide rules, you usually get about 2 digits of accuracy. Okay, so that's an approximation, though, like you would get on a calculator. Here I have a calculator. Let's see. So on the calculator, I'm going to compute 1.6 times 3.4. You can see it is a little bit over 5.4, but we did get accuracy to 2 decimal places at 5.4. Okay, so how do we do division? Well, we're going to find 9, essentially finding log of 9 on the D scale, distance from 1 to 9 on D scale, log of 9. I want to move back by log of 2. So log of 2 would be this distance from the 1 to the 2 on the C scale here. That would be log of 2. I want to move backwards that amount to subtract that distance. So what I'm going to do is actually, instead of finding the index and aligning that with the 9, I'm going to align the 2. Aligning the 2 with the 9 allows me to move the cursor back to the index, essentially subtracting that from log of 9. And then I see the result, 4.5, on the D scale again. So again, what you're doing here is essentially using the C scale to measure movement backwards along the D scale. So you see, I went from 1 to 9, that's log of 9 on the D scale. Then I went back, distance from 1 to 2, which is log of 2, and then on the D scale I should be showing distance from here to here, log of 9 minus log of 2, or log of 4.5. So to divide, instead of, after you find your first number on the D scale, instead of finding the index, you find the second number. So see, I've aligned 2 and 9. And then moved back by that log of 2 and found the 4.5. Now, there's another way to imagine what you're doing in terms of proportions, but I'll save that for another video. Okay. Let's do the second division example, example 4. So this one will be an approximation. So first I'll find log of 7.7 by coming out here to 7.7. Then I want to move backwards, log of 2.9. So I will align the 2.9, which is here. Okay. So from here to here, log of 7.7. Then moving back to this 1, that's subtracting log of 2.9. Aligning the cursor. And then I'm going to read that result as 2. This is 2.5, 2.65. It looks a little bit to the right, but I'm going to interpret that as 2.65 approximately. Let's see what we would get here. Computing 7.7 divided by 2.9, 2.655. Okay, so that 5 should probably be a 6. But to be safe, I could simply do 2 places accuracy. Okay, so let's see what else could happen. You might have already noticed that there is an additional problem you can have, which is that your calculation can take you off scale. In other words, what would happen if we tried to use the method already described for computing 4 times 6? I would want to compute log of 4, which is distance from 1 to 4. Okay, distance from 1 to 4. Then what I want to do is add log of 6, which is the distance along the C scale from 1 to 6. Now the problem is 6 is all the way over here. So physically log of 4 to here, then log of 6 added to that would bring me out to here. Now the key to understanding what to do here is understanding that the C and the D scales essentially repeat themselves infinite infinitely in both directions. So attached to this one is really the same as this one, and then what really happens here is there's another copy of the D scale there. There's another copy of the D scale. You can actually see it with the marking here. See the 9 where both my fingers are? A copy to the left of the 1 here, and they continue in both directions, just being pasted one to one. Okay, so the trick is what to do in this situation. Well, this one is essentially the same as this one. So what I'm going to do is switch the ones. What I'm seeing now really is a copy of the next order of magnitude, which is represented by what we thought of previously as this D scale being over here. So I switch the ones because really I have copies of everything in both directions, so 1, 1 is as good as the other one. Then I find the 6. And then you can see what I'm reading here is 2.4. I'm a little bit off because of how bad a job I did of setting it, but what I'm reading is 2.4. Now, we know the answer should be 24, and the key is, if you think of how I had it lined up originally, going to 4 and then going out to 6, what happens is I go to this next copy of the D scale, which represents the next order of magnitude. So 2.4 should be interpreted as 24. And now what's the reason for this? The reason is the log we're really using is a base 10 log. So log of 4 plus log of 6 is really log of 24. But log of 24, because think of that as log, think of an intermediate thing here, this is the same as log of 10 times 2.4. And so I'm using base 10 log, so log of 10 is 1 plus log of 2.4. That's what I'm reading. Right? So the 1 was because I went 1 entire scale length and then added log of 2.4 and ended up at the 2.4. So this 1 is what's called the order of magnitude, or the exponent. If you think of scientific notation, that's this exponent here. And then the other number, the log of whatever, is sometimes called the mantissa. That's always between 1 and 10. So if you write a number in scientific notation, you should have something between 1 and 10, but not including 10, right? So you should have something like 2.35 times 10 to the whatever, right? That whatever is going to tell you the exponent, or which copy of the scale you're on. And then this number is always on the scale, so you might have thought it was weird at the beginning, right? Why is there no numbers between 0 and 1? Well, any number when you write in scientific notation always has this number to the left of the decimal point, which is not a 0. So you can find that on the slide rule. Okay, now let's see what would happen for division. For division, let's try 3.3. Here's 3.5, 3.4, 3.3. Now remember, to divide, I want to align the 8.5, only needs to move a little here. I want to align the 8.5, and what we said about division was we want to measure that backwards in this direction, back to this 1 index. Now you can see that's off the scale. But the nice thing about division is that I don't have to reset the slide when I go off scale using this technique, because the other index is already on the right. So remember, for division, you align the second number instead of the index, and then you search for the index. You should really be going to the left, but what we see here, right now, we're interpreting this D scale as the copy of the D scale which is over here, and this 1 is the same as this 1. Okay, so that 1 would be over, let's find it here with the cursor. You can see that 1 is over 3.9. But I interpret that as 0.39 because what happened was I went off to the left and I got the next order of magnitude down. So instead of 3.9, it means 0.39. Okay, so the nice thing for division is you actually don't have to reset and use the opposite index. You just find the one of the two indices with the cursor that is available to you. Now, let's do some common problems. So here I'm going to use the slide rule to do these two problems in kind of the common way that you would do them. So maybe this is not the best. Let's get another sheet here. Okay, so the question is, how am I going to do 42 times 932? Now let's just do this on this sheet. What I'm going to do on the slide rule is I'm going to do 4.2 times about 9.3. Because first of all, on this slide rule, I can't deal with this 2 here very well. It's just going to be too fine a calculation to make. But let's do that. So let's do the 4.2. Here I find the 4.2 on the D scale. Then I need to align one of the indices to it. I'm going to align the right index, already seeing that if I align the left index I'll be off scale. Okay, so I align the index. Then really I'm going to the right, but I'm going to the next order of magnitude and then ending up at the 9.3, which is here. And reading the result on the D scale, I read the result as about 3.9. So what I would do then is I would write 3.9. Now, what most people do when using the slide rule is they write the 3.9 and then they compute the order of magnitude. So I would do that by saying, well, 40 times 900, that's going to be 36,000 approximately. So what this should be is 39,000. Okay, so I compute the order of magnitude by estimation. Let's do one with division. So here, what I'm going to do is for the next one, I'm going to, on the slide rule, do about 4.7 divided by 7.5. Again, I can't really deal with that 8. I could set it a hair under the 4.7. Maybe we can try that. So let's see, here's 4.5, 6, 7. I'm going to set it a hair under to try and get that next digit accounted for. A hair under 4.7. Then I'm going to align the 7.5. And we know, really we should imagine that we're going to the left, 7.5, and finding this 1 here. Of course that's off the scale, but that's the same as this index here. So there is a 1. And I read about 6.2. So what I would do then, reading 6.2 on the D scale, is I would write, okay, 6.2. And then I would interpret the order of magnitude. Here, if you had about 500 divided by 7, you're going to get something with 2 digits. So 62 is actually correct here, and I don't make an adjustment of the decimal point. Okay? So I hope you enjoyed this video of the theory behind the C scale and the D scale and how to use them. I'll have more theory and use of the other scales in future videos. Thanks for watching.